In this video, we're going to look at rational functions. A rational function is a function that's a ratio of two polynomial functions. F of x is equal to P of x divided by Q of x. In this video, we're going to review how to graph a rational function. The first step in graphing a rational function is to find the domain by setting the denominator equal to 0. This gives you the restrictions, but then can also be translated into interval notation of the domain. So just depending on what the requirements are for the problem, sometimes all we need to know is what x cannot be. Once you've found the domain, we want to factor and simplify the function as much as possible. Everything else that we do for graphing this rational function can be done from that simplified version of the function, with the exception of finding the domain. The domain has to be done before you start simplifying. Once you've simplified, you're going to identify any holes. A hole is a 0 from the denominator that simplifies out. This is called a removable discontinuity. To find the ordered pair of the hole, you plug that back in the value of that removed 0 into the simplified function to find that ordered pair. Once you've identified any holes, you're going to find your vertical asymptotes. These are going to be the zeros of the denominator after it's been simplified. So they're the remaining zeros, the holes being the other restrictions. So all of your holes and vertical asymptotes are going to match your list of restrictions from that very first step. Then you'll identify horizontal or oblique asymptotes. To do this, we're comparing the degree of the numerator, we'll call this n, and the degree of the denominator, we'll call this d. If the degree of the denominator is greater than the degree of the numerator, so if d is greater than n, we call the function bottom heavy, and it's going to have a horizontal asymptote at y equals 0. If the degrees are equal, so if d is equal to n, then the function has a horizontal asymptote at y equals the ratio of your lead coefficients. So the lead coefficient of your numerator over the lead coefficient of your denominator. If the degree of your numerator is greater than the degree in your denominator, then the function is top-heavy and there's no horizontal asymptote. If the degree of your numerator is 1 more than the degree of your denominator, then we have an oblique asymptote or a slant asymptote. And you're going to use division to find that oblique asymptote. What you'll end up doing is divide the equation. So you'll divide the numerator by the denominator. And the oblique asymptote is equal to y equals the quotient ignoring the remainder. Once you've determined all of the asymptotes, you'll find the x and the y intercepts. And then you might have to find some additional points if necessary to determine the behavior of each branch being each part of the graph that's separated by vertical asymptotes. All right, so let's go through one together. Sketch the graph of the function r of x equals x squared minus 4 divided by x squared minus 7x plus 10. To find the domain, and we know that we're going to end up simplifying this, let's go ahead and start factoring everything. So we're going to factor the numerator and the denominator. X squared minus 4, that's a difference of 2 squares, so that factors to x plus 2 times x minus 2. And then x squared minus 7x plus 10. We need factors of 10 that add up to -7. That's going to be -5 and -2. Now, this requires a little bit of patience. We see those factors of x minus 2. We want to make sure we don't cancel those out yet. Let's start by stating our domain. So for our domain, we can see that x cannot equal 5 or 2, and those are the zeros that we get from our denominator. Now, if we wanted to write this in interval notation, it might help you to see it on a number line. So I might sketch 2 and 5. And really, these are the only values that x cannot be. It can be everything else. So that's going to be from -infinity to 2, union 2 to 5, union 5 to infinity. So again, depending on how the question is worded or what they're looking for, sometimes it's enough just to state the restrictions as the domain. Other times they want the domain in interval notation. And now that my domain has been stated, I've identified all of my restrictions. I can go ahead and simplify. The x minus 2 factor simplify to 1. So my function r of x simplifies to x plus 2 divided by x minus 5. Now the next step is to find our holes. We can see that we removed this discontinuity at 2, so that's going to end up being a hole. And to find the ordered pair for that, we're going to just plug 2 into that simplified version of our function. So that's going to be 2 plus 2 over 2 minus 5. Or 2 and negative 4/3. So when we go to graph this, we are going to plot this, but we're going to plot this ordered pair as an open circle. All right, now that we've identified our holes, the next are our vertical asymptotes. Our vertical asymptotes are now at the zeros of our denominator when it's simplified. So that's going to be at x equals 5. For our horizontal asymptote, we're looking at the degree of the numerator and the degree of the denominator. Since they are both 1, that horizontal asymptote is at y equals the ratio of our lead coefficients, which was 1 over 1, or just 1. To calculate our x-intercept, this is going to be where the numerator equals 0. So x plus 2 equals 0. X is equal to negative 2. And we can write this as an ordered pair, negative 2, 0. For the y-intercept, you're going to plug in x equals 0. So y is equal to 0 plus 2 over 0 minus 5, or negative 2/5. And that ordered pair is written 0, negative 2/5. And I'm going to stop here. I'm going to put all this on my graph to see what I can already graph and if I need additional points. So I'm going to start by plotting my asymptotes. I'm going to use a solid line just because it makes it a little bit easier to see on the screen. But typically we would use a dashed line. So our vertical asymptote is at x equals 5. There's our vertical asymptote. Our horizontal asymptote is at y equals 1. We have a hole at 2, negative 4/3. So negative 4/3 is about negative 1 1/3. So we can approximate that point about there. Actually, let me use a different color there. Our x-intercept was negative 2, 0. So there's our x-intercept, and our y-intercept was 0, negative 2/5. That's about there. So our asymptotes, if you recall, kind of shape the behavior of each branch. So my graph, this branch over here is going to look something like this, where it approaches both of our asymptotes without touching them. From here, we can see we don't have anything over here. So our right branch, we don't have any ordered pairs for, so we don't really know where it goes. It could be up here. It could be down here. We don't know. We're going to have to end up finding an additional point now to make sure that we know where that right branch is located and what its behavior is going to look like. So picking an x value on that right branch, that's going to be something greater than x equals 5. Let's find f of 6. And again, I'm using that simplified function. So this is going to be 6 plus 2 over 6 minus 5. And that's going to be 8 over 1, or just 8. So that tells me I've got a 0.68. And just that 1 point alone can determine that the shape of this branch is going to be decreasing in that top quadrant.